I now want to talk to you briefly about the exact procedures for extractions. These represent sort of a generalized set of instructions that you can use any time that you need to do an extraction. All you would need to do is know what solvent you were using and what solute and system you were going to be working with. On the small scale, we use centrifuge tubes to do our extractions. Centrifuge tubes look like test tubes, but they come down to a conical point at the bottom. So, very quickly, we obtain a clean screw cap centrifuge tube. We want to use a screw cap so that we can seal it up and shake it. We transfer our solution to be extracted into the centrifuge tube. We then add the second layer of extraction solvent. We then cap the tube and gently rock for a few seconds, and then loosen the cap to prevent the pressure buildup. We then tighten the cap and repeat these two steps until no more pressure buildup is released. We can recognize that pressure is being built up because when we open the cap, we should hear a small hiss as the excess pressure is released, similar to what happens when you, for example, open a soda pop can. After the pressure has equilibrated, we then gently shake that tube for 1 to 2 minutes. The longer we shake, the more opportunity there is for the solute to contact with an interface layer and move into its desired solvent. We then let the test tube or the centrifuge stand until the layers separate. If we're having problems getting the layers to separate, we can put the centrifuge tube into a centrifuge for a few minutes and then examine it. We just keep centrifuging until the separation is complete. Then we use a pasteur pipette and we remove only the bottom layer. This is made easier by the fact that the tube tapers, so that all we really need to do is make sure that we don't suck out any of the top layer. We remove that layer and transfer it into a separate container. Then we can remove the top layer, put that in a different container, and then sometimes we want to do multiple extractions for the reasons that I showed you earlier when we did our calculations. So we would take whichever layer was being extracted, we'd put it back into the centrifuge tube, and then repeat this process. One thing that I will warn you is that it's a really good idea to save all of the layers that are removed during this extraction process, even the one that we're not working with anymore, just in case we get confused and we accidentally move on with the wrong layer. If we've saved all the layers, we discover our mistake, we can go back and get the correct layer and not have to start entirely over. On the large scale, which we'll be doing later this semester, we use a special piece of apparatus called a separatory funnel. It's often sort of acronymed a SEP funnel. This is a separatory funnel. We'll talk about this again in a later experiment, but basically a separatory funnel has sort of a pear shape. It tapers down at the bottom. It has a valve, which we call a stopcock, allowing us to open and remove liquid from the bottom and close up. It has a stem that the liquid flows through. It has an opening on the top that we can seal up with a stopper. In order to use this, we securely fasten the funnel, or sometimes we stand it up in an iron ring. We make sure the stopcock is closed. We place a beaker underneath the funnel just in case it leaks. We then pour our solution and the extraction solvent into the funnel. We stopper the funnel securely. We turn the funnel with one hand and gently rock the funnel, and then we turn it upside down and open the stopcock. When it's upside down, the liquid will be on the bottom, far away from the stopcock. So opening the stopcock will release pressure. We then open the stopcock to vent the pressure, watching for a release of gas. We then repeat these steps until the pressure is released. Again, we shake after that for 1 to 2 minutes. We then replace the funnel in its clamp or iron ring, and we leave it to stand until the layers separate. Once the layers are separated, we remove the stopper, and then we drain the lower layer out the bottom. We do not, however, drain the upper layer out the bottom. It's best practice to pour the upper layer out of the opening in the top. The reason for this is that we don't want any of the liquid that might be adhered to the side of the separatory funnel to be dragged out by the upper layer as it exits. So best practice is bottom layer out the bottom, top layer out the top. Finally then, I want to talk to you about acid-base extractions. If we look at organic substances, they generally have a relatively low solubility in water. However, it is possible to change the solubility of substances by having them do a chemical reaction and convert from being an electrically neutral molecule into a charged ion. Ions, ionic substances, generally have a high solubility in water. If, for example, we have an organic acid, a carboxylic acid, if this has a very long carbon chain, it will not be very soluble in water. However, if we treat it with a base, deprotonating, removing that hydrogen, we would then be left behind with a negatively charged oxygen, which would then make this entire particle an ion. There would also be presumably a counter ion associated with it. This ionic substance then should be more soluble in water. So therefore, it might start in its neutral form with a high solubility in the organic phase, but then by deprotonating it, it might have a high solubility in the water phase and prefer to move into the aqueous layer. If we wanted the acid afterwards, we could treat that aqueous solution after separation with a strong acid to put a proton back onto the carboxylic acid carboxylate ion, and then extract with organic to get it back into an organic layer. That would look like this. We can do a similar thing with organic bases. Probably one of the most common type of organic bases is the amine, where we have a nitrogen attached to one or more carbon groups. For purposes here, we've just shown one carbon group and two hydrogens. Amines are bases because they have a lone pair that can make a bond to a hydrogen plus from an acid. So for example, this lone pair could remove one of the hydrogens from hydronium ion. That again would create an ion, in this case a positively charged ion, and of course there would be a counter ion associated with that, and that positively charged ion would be soluble in water. So we could extract that from the organic, and then if we wanted to get the base back, we could simply add a strong base to deprotonate this organic ion, converting it back to a neutral, which would be soluble in the organic layer. When we do an extraction, we sometimes use sort of a flowchart diagram to represent how the various operations are moving the substances around, which substance ends in which layer. Here's an example of an acid-base extraction. So let's assume that we have a mixture of three substances: a neutral substance, an organic base, and an organic acid. Let's put them all into an organic solvent. So this would be an organic solvent. we would see then in our container of organic solvent, we would have solvent plus these three substances. If we then extracted that by mixing it with an immiscible aqueous layer containing strong base like sodium hydroxide, we would expect the sodium hydroxide to react with the carboxylic acid, deprotonate it, and convert it into an ionic substance. If we then shook that mixture, the organic carboxylate ion substance should move into the aqueous layer. I have it here pictured with a sodium counterion that we got from our sodium hydroxide base. And then the organic layer would continue, and then the other two substances would remain in the organic layer because they presumably are more soluble in organic than aqueous, as they are. So by separating the two layers, we would have separated out the carboxylate. We could then treat that aqueous layer containing the carboxylate ion with a strong acid like aqueous hydrogen chloride and put the proton back onto the carboxylate, regenerate the organic soluble acid, extract that, isolate that. Our organic solvent could then be extracted with strong acid. So we used base first, acid. And there's no rule about what order to do these in. This is just showing how these things would flow. By treating it with strong acid, the amine base would deprotonate the strong acid. It would become an ion. It would prefer to exist in the aqueous layer, so it would move to the aqueous layer that's formed when we add this. And then when we separate the two layers, we would get the organic base as an ion in the aqueous layer, and then the only thing remaining in the organic solvent would be our neutral substance. So you can see that basically, I don't have a step here, but if we were to treat this with sodium hydroxide, we could deprotonate this, and we would have separated those three substances into three separate containers. This is essentially what we're going to be doing in our experiment for extraction.